Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we are going to continue our discussion on particle dynamics, starting with force fields, linear and quadratic friction forces and laws of gravitation. So thank you. So let us continue. So we have our focus on particle dynamics. And the key concepts we will be focusing on will be on equations of motion of the system, the equations of motion, and we'll talk about force fields. Well, we have already spoken about force. What is this new issue called field? So we will briefly spend some time on this issue. How is force a field? It turns out that force is a field, but not friction. Friction is not a field, right? So we'll talk about the impact of frictions, linear and quadratic friction forces. Okay. So let us continue from the point where we introduced Newton's second law, which says that if we have a body of or a particle of mass m, then the net acceleration of the particle, so the net acceleration is rate of change of velocity of the particle, is going to be the sum of all the forces which are acting on the particle, right, and so on. Okay, and typically we see that this is going to be the independent variable in this equation of motion is the time t, and we typically solve for the velocity v, and when we typically have that these equations are ordinary differential equations, first order ordinary differential equations in the independent variable t, right? Okay. So this question is, we have more than enough number of times we have always referenced even bodies as particle. So what is the difference between body and what is the difference between particle? I think now is the time that is correct to distinguish a particle with a body, right? So typically I would say a body is a collection of particles which are connected to each other with rigid inextensible light rods, right? So if I say we have n particles, right, and these particles are connected to each other with let's say rigid inextensible rod, then this collection of particle is said to be body, right? Now I have to quantify the words rigid, inextensible and light rods, right? So let me write down what I just said. So this question that we are trying to answer is, when can real bodies be modeled as particles, right? Real bodies be modeled as particles. The answer lies, as I just said, is that rigid bodies, we are not in this entire course on mechanics of bodies, we'll only talk about rigid bodies. We try to refrain from elastic bodies discussion. So rigid bodies without rotation, rigid body without rotation can be treated as, well, that's the other way around. So what I am writing is the other way around. When can a rigid body be treated as a particle? So right now what I just said is, what is the difference between particle and a body, right? So rigid bodies without rotation can be treated can be treated as a particle with its mass at its center of mass, at its cm. So suppose we have a rigid body. I want to describe the rigid body using the equation of motion, right? And typically we want to when we talk about equation of motion of the rigid body, that is typically for the case of particles. So what I just said is we can transform a body into a particle for the sake of the kinematics by just focusing on the center of mass of the body, right? Not the center of mass may not be necessarily be the geometric center, but the center of mass. And then we can say the point which is the center of mass is the particle equivalent of the rigid body, right? So that is what we do when we model the rigid body as a particle. Okay. So then let us start with our discussion on 1D equations of motion or rectilinear motion. So what am I saying? So we are going to start describing the rectilinear motion in a force field. The rectilinear motion in a force field. So that is the 1D motion of the object in the presence of a force, right? So in short, this is a 1D motion. Okay. So before doing that, let me just touch upon the topic of what is a field. So why is force a field but friction is not? It turns out fields are vectors which depends on the position of the particle, and it does not depend on velocity or any other quantity. So in that regard, we know that force depends on the position of the system, right? The force depends on the position, and and on the other hand, the frictional force, they do not depend on the position but on the velocity, and hence friction forces are not fields, right? So a force, so let me write down what I just said. A force is a field. A force is a field if it depends. A force is a field if it depends on the position. If it depends on the position of the particle, right, and not on velocity or time. If it depends on the position of the particle and not on the velocity and the time of the particle, right? So example is the gravitational force is a gravitational force field. The gravitational force. So it depends on 1 over r square. So it depends on the position of the two particles, right? But on the other hand, a case where we have, which is not a case of field, is the frictional force. Frictional forces are not fields, and the reason is obvious, because friction forces depend on the velocity of the particle. We are going to see some of these examples. So let us look at some basic equations of motion in 1D to understand how we are going to solve a typical problem, right? So let us look at this example to begin with. Vertical motion under gravity. Right, vertical motion under gravity. So we have a particle which is projected upward, right, and then we expect that the particle is being acted upon by gravity, so it has to come down sooner or later. So the problem says is, let us say the particle is being projected upward with some initial velocity at t equal to 0, then what is the maximum height of the particle? that it attains, and also what is the total time of travel of the particle, right? So that is what we have to find. So a particle is projected vertically upward with speed u, right, and moves in a straight line under gravity. Moves in a straight line under gravity with no resistance. So we in this problem we assume that as if the particle is moving in a vacuum, right? So there is no air resistance, and then we have to find the maximum height, and the time taken and the total time of flight. Total time of flight means the flight taken by the particle to move up and then move down, the total time. Okay, so the particle, when it is traveling, the only force acting on the particle is its weight, which is acting downward, right? So we can quickly write down the Newton's second law. It says that m times dv dt is equal to minus m times g. We can assume that our positive z axis or positive direction is the upward direction, right? So this is my second law here, and from here I can find that my velocity v of t comes out to be, minus, we integrate this equation, minus gt plus a constant of integration, which is c. Now we look at the initial condition. The initial condition is at t equal to 0, we have the speed v is u, it moves with the speed u, and of course the distance traveled at t equal to 0, x is equal to 0, right? So at t equal to 0, v is u, so c becomes u, and we have that v is, the constant can be found, and we get that the solution is gt plus minus gt plus u, right? And what we have is, let us see the total time of flight. From here we integrate this equation. We see that dx dt is minus gt plus u, and from here we can quickly find that x is u. Well, I should say the direction along the vertically upward direction is the z. So let me call this as z. So dz dt. So z comes out to be ut square, ut minus gt square by 2. We have already used the initial conditions here. At t equal to 0, z is 0, right? The particle starts with 0 to begin with. So from here we have to derive two things. Find the maximum height. So the maximum height, when do you think? So this is a typically physics oriented problem. The readers are requested to think a bit. When do we think can the body achieve the maximum height? The answer lies that the maximum height is going to achieve when the body keeps on traveling until it stops at some height, and then it starts to fall, right? So we have to find the height at which the body is going to stop before it changes direction of its motion, right? So we set, to find the maximum height, we set v equal to 0, and to find h max, we set v is equal to 0, but v is equal to u minus gt, and from here we get that the time at which the height is attained to be the maximum is u over g, right? And we plug u over g we plug the time over in the formula of z of t, right? We see that what is z of t? Z of t is this quantity, and we plug t equal to u over g, and we see that z, which is the maximum height, is what we get is coming out to be, after plugging t equal to u by g, we get that z is u square by 2g, and that is the maximum height. Now, to travel the maximum height, the time taken by the object is u over g, and then it has to again come back the same height, that is travel the same distance, and so we expect the time to be the same, that is u over g itself. So the total time of flight, or the time of flight, will be the time which is twice this value, and hence that is the total time of flight. Well, readers who don't understand or don't believe what I just said about the time of flight can quickly find the time of flight from the formula itself. So this question is, to find the time of flight, we are going to set z of t equal to 0. Why? Because the time of flight is when the displacement of the particle is 0. So either it starts at t equal to 0, the displacement is 0, so it starts, or it ends when it has gone up and gone down, then the displacement is also 0. So from the formula, this is ut minus gt square by 2, and we see that there are two times when the displacement is 0. One time is 0 and the other time is the time of flight that we are trying to find. So we find the non-trivial t, and we find that t comes out to be 2u over g from here, and that is indeed twice the time it takes to reach the maximum distance. Okay, so that was a simple problem. Let us look at one associated problem in this projectile motion. So now let us come back to that elevator problem we discussed one or two modules back. So again, we have an elevator which is doing its job, and suddenly the cable of the elevator is cut, right? And we have an individual which is inside the elevator, and we want, now this question says, see, what we expect is that when we cut the elevator cable, the elevator is going to come down with an acceleration of minus g, right? And the person inside the elevator, of course, will feel weightless. But this question is, the moment the elevator hits the ground, it is going to make an impact, and with that impact, the same impact will fall over that person, and he or she is going to get hurt, right? So this question says, suppose we know that after cutting the cable, the elevator is going to travel downward, but suppose the individual jumps upward, right? So suppose the individual jumps upward, then it is going to cancel the motion of the elevator, and this question is that, is there any critical velocity with which the individual should jump upward so that he or she is not hurt, or its net relative velocity is 0, right? So that is when it does not get hurt. So this question is, again, an elevator is snapped, and heading to the ground, right? Without speed, should the occupant jump, sorry, with what speed should the occupant jump so as to avoid the crash, right? So as to avoid the crash. So it has to jump against the motion of the elevator so that the individual is not impacted, right? So basically we have to find, given a distance traveled, we have to find what is the speed of the elevator just before it hits the ground, and of course the individual is going to jump with exactly the same speed in the opposite direction, so that the net speed of the system is 0, right? And the individual in that way is going to avoid the crash. So let us find the the speed of the elevator before hitting the ground. So let us say that we have a height of h to cover by the elevator before it hits the ground, right? Let the elevator cover height h. Let the elevator cover a height h when the cable is cut, right? Let the elevator cover height h when the cable is cut. So what we see is that the distance that it has to travel, the distance the elevator has to travel is h, of course, right? And we can think of this problem of this elevator traveling as the motion of the projectile in the previous problem, where we only look at half the problem. That is, before cutting the cable, the elevator is at rest, right? So we can think of it equivalent to the ball problem, where the ball goes up, then stops for a moment before starts to go down. Here the elevator is already stopped at t equal to 0, and it directly starts to go down. So this is half the problem of the ball problem that we discussed few minutes back. So at t equal to 0, the height it has to cover is h. Let me call this as the maximum height covered, or the maximum distance covered, right? And from here we can find that h is going to be u square by 2g. That is from this formula of the ball formula, right? From here I see that the u max comes out to be square root 2gh, right? And which means that this is the velocity or the speed with which the speed in 1D. So this is the speed with which the elevator is hitting the ground, which before traveling a distance h, and we have that the individual should jump. So the occupant should jump with a speed square root 2gh upward, right? That is in the direction opposite to the elevator, in order to avoid the crash. Okay. So that is the problem. Now let us look at another problem of a rectilinear motion of a projectile. That is, if suppose we have the same ball problem, and now the ball is being thrown at a massive speed, let's say such a high speed that perhaps the ball is able to escape the gravitational force of the earth, right? Then we have to describe the motion of the ball. So what we are going to do is, we go back to the ball problem again. So we have again a particle of mass m, and this is moving under gravitational force of mass capital M, right? So we have a large body of mass capital M, let's say Earth, and then we throw the ball upward, which is having a mass small m, right? So let us say we throw from the surface here, right? So that is a particle of mass small m. Okay, and then let us say this is fixed at the origin. Okay. So let us say my origin of this large mass capital M is at the center of this mass. So this is my O, which means that the mass small m, the particle of mass small m, is at a distance a, where a is the radius of the earth, right? So a is the radius of the earth. So initially the particle P is at a distance a from the origin O, right? So it has a distance, let's say the distance is equal to the, well, of course, the distance from the origin of the frame that we have fixed. So it is at a distance A from the origin, and then it is projected with the speed u. So this is all happening at t equal to 0. When it is projected with speed u, right, and away from the origin. So we have to find the condition that P escapes, to infinity, right? That is, we have to find the condition that the ball, when thrown from this starting point, never comes back, or its velocity always continues upward, right? It never stops and never turns around and comes back. That is the condition we have to find. So, well, this is a question of gravitational force field. So we set up the Newton's law, right? So the Newton's second law says that the total mass times acceleration of the particle m, well, we drop this this bar here because we are talking about the motion in 1D here in the z direction. So m dv dt is equal to minus small m capital M g by r square. So that is my gravitational force, where r is any distance starting from the origin O, right? So from here we see that this is m times dv dt. What have we got? We see that we can use chain rule. I don't want to integrate this problem with respect to t, because t is not there on the right hand side. It is implicitly hidden in the variable r and r, that's all. So I change the independent variable as m dv dr times dr dt, right? But what is dr dt? Dr dt is the velocity or the speed here, in this case v. So we have that this is m times v dv dr, and this is equal to minus mg by r square. Now we can integrate this equation of motion, and we are going to get we integrate this v from the initial speed is u, and the final is what we have to find, and at t equal to 0 the initial radius r is a and the final radius r is r. That is what we have to find. Okay, so once we integrate this, we get this following solution, that v square is u square minus 2 mg by a plus 2 mg by r. So that is the final answer after integration, and there is a specific reason as to why we have written this final answer in this specific. We have clubbed two terms specifically. Now notice that, let me call this first term as 1 and the second term as 2. Now notice that the second term is always positive for all r, right? But suppose, so which means that this second term is only going to contribute to positive values of v, right? Now what do we want to find is, we want to find that critical velocity, right? We have to find the critical condition when the particle, beyond the critical condition, the particle is going to escape to infinity, and before the critical condition the particle is going to stop and come back to the earth. Now it turns out this second term is can be negative if I have that u obeys this following condition, right? Now if we want that the particle comes back, if we want that there is no escape to infinity, then we must have that there will be some, look, if both the terms, suppose term 1 and term 2, both the terms, well, term 2 is always positive, even term 1 is positive, that is, if this quantity, if u square is greater than 2 mg, so what we see is term 1 plus term 2 both are positive, we see that v square is positive, and there is no instance that that the particle is going to stop, right? And which means that the particle is going to go to infinity. It is only when we have that first term which will be negative that we can have some criteria of stopping the particle. I repeat that if both the terms are positive, we expect the velocity to be positive and the particle is going to continue forever and escape to infinity. It is only when you have this second term is anyway positive for all values of r, because r is positive and everything else is positive in the numerator. But the first term can be negative, thereby allowing the v to be 0 and allowing the particle to stop and not escape to infinity if we have this following, right? And in this case, this is my condition, this is my required condition, right? That the particle escapes to infinity. Okay. So what have we got here? So let us continue. So now we talk about, so we have already found the condition, so let us talk another section of this problem. The next part, let me call this as example number, maybe this is already example number 2 in the module. So let me now look at example number 2a, that is, the problem is getting extended here. So suppose my initial speed of throwing the particle or object u square is mg by a, right? And we have to find the distance, the max distance from the origin O achieved by the particle p and the time taken to reach the position, Find the maximum distance from the origin and the time taken to reach that position, the time. So again, we recall that my velocity formula was u square minus 2 mg by a plus 2 mg by r. Now if we plug u square equal to this following quantity, we are going to get the value of v, and v square comes out to be mg times 2 by r minus 1 over a. So we have to find the max distance from O. The max distance is going to happen when v becomes 0, after which the v is going to change, or the velocity of the particle is going to change direction, right? So this is when max distance when v is 0, and from here I see that r comes out to be 2a, twice the starting distance is when we get the max distance, right? And similarly, we have to find the time taken by the particle to reach that position. Now to do that, we have to integrate this particular equation. So we integrate this. That is dx dt whole square is mg to r minus 1 over a, and again we see that on the left hand side we have a time t, and on the right hand side t is not present explicitly. So we have to again change our equation of motion. So dx dt is dx dr times dr dt, right? And well, that I should say this is not x but this is z, the max distance or the time. Hold on, I think we need time, the time taken by the particle to reach that position. So we keep the equation in time. Okay. We keep our equation of motion in time. So it is dz dt. And Well, we have a r sitting here. Well, what is r? I think z is r itself, because we have an equation, we have a 1D motion. So r is nothing but the distance traveled along the vertically upward and downward direction. So this is dr dt. So from here we just have to integrate this. We see that r has to be integrated dr times whatever quantity is here. R is from r equal to a to r equal to 2a, and from here time t is t from 0 to t, right? So times dt. And from here we can, after integrating, we can find quickly that the solution is t comes out to be square root a cube by mg times 1 plus pi by 2. Okay? See how much time? Well, I think this is where I stop this first module, and in the next module we will start with our discussion of the motion on an inclined plane. So thank you very much.